Let's consider a pulley which is rotating around its center. There is a force acting on it. So let's say that there is a rope hanging on one side, and you just pull this rope, and the force is given by the, let's say, the tension force, and this tension force has a magnitude of 15 newtons. Now this pulley has a mass of 4 kilograms, and its radius is given by 33 centimeters. And of course there is the frictional forces acting on the system, and those frictional forces create a torque of 1.10 meter Newton. And it is observed that under the influence of this force, the pulley accelerates from 0 to 30 radians per second. So its angular velocity changes from 0 radians per second to 30 radians per second in 3 seconds. So what is the moment of inertia of this system? Now, to calculate the moment of inertia, we can use the torque angular acceleration relation. So if we know the torque, we know the forces acting on the system. So there is this force which will create a torque, which will be given by 15.0 Newton. It is acting at a distance of 33 centimeters, or 0.33 meters. And there is a frictional torque. The frictional torque will try to stop the rotation, and hence it acts in the opposite direction as the torque created by this force. So let's put a minus sign, 1.1 meter Newton. And the total torque of the system is 3.38. 3.85 meter Newton. So this is the total torque acting on the system. So we know the torque. If we would like to determine the moment of inertia, we need to determine the angular acceleration. Well, the angular acceleration, if we assume it to be a constant, the forces are given as constant, and hence the angular acceleration will also be constant. The angular acceleration will be the final angular velocity, which is 30.0 radians per second, minus the initial angular velocity, which is 0, divided by the time in which this change happens. It's given as 3 seconds. So the angular acceleration is 10 radians per second squared. Now we know everything we need to determine the moment of inertia. The moment of inertia of the pulley will be equal to 3.85 meter newtons divided by the angular acceleration, which is 10 radians per second squared, or 0.39 meters newtons second squared, 0.39 kilograms meter squared. Or if you want to keep all the digits, 3.85. 0.385. Now, note that, well, this is the measured moment of inertia. Now, if the pulley was just a uniform disk of given radius, its moment of inertia of this cylinder is given by half its total mass times its radius squared. Now, we know the mass, we know the radius, so this is 1 over 2. The mass is 4 kilograms. The radius is 0.33 meters squared. So for a cylinder with the same mass and the same radius, the moment of inertia would be 0.218 kilograms meter squared. Now, note that the moment of inertia for a homogeneous cylinder is less than the moment of inertia of the pulley, which basically tells us that the mass of the pulley is more concentrated at the outer rims of the pulley rather than at the center. Now, if on the other extreme, if this was not a disk but just a ring, all the mass concentrated at the edge, in such a case, the moment of inertia of the ring is mass times the radius squared. Since all the masses are at the same distance given by the radius of the ring, the moment of inertia of the ring is just its mass times the radius squared, which will give us a moment of inertia of 0.436 kilograms meter squared. So you see that the moment of inertia, the measured moment of inertia of the pulley is somewhere between the moment of inertia of a uniform cylinder and the moment of inertia of a pure ring. And hence the mass distribution is such that it's not uniform. More mass is concentrated at the edges of the ring, but not all the mass is actually on the edge.